then what would just a line be?
Okay.
No, I'm just. You know what I mean? Like when you say just a line, what do you mean by that?
Well, you get to look at that and not see it as anything else,
Right.
like
Okay.
a single line.
Okay.
Maybe it was 2 points on it.
Okay.
Yeah, whereas like with the dot one, the other one is just there's a section up each line. I feel like students be able to stop pointing directly to the time and the amount. It's not just a line.
Right.
There's a bunch of
Don't look at these yet. I'll tell you when we're going to start these. So keep talking.
So it's like
Make your list.
if there's the line, then it's just the change, or there's just the rate of change. But as like the other one shows,
So this one shows the rate of change.
yeah, like it's showing that the
I
points
like
are
how it shows the
line.
relationship between the change.
This one shows how the end is very how it affects. Yeah. But this one seems like an abstract where we're trying to find specific. And it shows that it's really an increase. It shows the relationships between like no, like you know, if it's a positive line, it's an increase. It really shows it because the activity goes up.
I was like in my class and they were learning about how functions are positive and negative, how are increasing and decreasing, and the kids had the hardest time taking that apart. But probably because also the graph is static.
We always did. If you're running up a hill, then you got the corresponding points.
Right. And that's what's running up the hill.
Yeah. Those are increase. It's the other way. You're running down, be like going down.
What does lawn mowing have to do with running in hills, right?
What does what have to do with running?
Lawn mowing, right? This is about mowing the lawn, right?
Right. Just lawn mowing the hill.
I mean, that's where kids go, right?
Lawn mowing upwards.
Yeah.
That's what the
Shade
Redskins
thinking.
is doing. I guess we could say that as the triangle increases, the area of the mowing is increasing too.
This one shows that she's actually moving like that.
Oh, so maybe we should refresh like what these were. What were the quantities? What's the quantity on the x-axis?
How many hours have passed?
Minutes?
Yeah, minutes. It was minutes after. But I didn't give you an x-axis, so it could have been that m not going to be any number of minutes after noon. And then what was the y-axis?
Total number of lawn tree mowed.
Yeah, total number of square feet of lawn. Okay, so you can, if you want to take one more minute. So it's number of minutes, but it doesn't have to be 10. It could be any, starting anywhere m naught. And then the y-axis is giving total amount mowed in square feet.
What are the areas that mine was?
One half base times height.
Yeah, I don't know what that is. 1/2 base of
1/2 dm times dl. All right, so let's talk. What's one thing you guys came up with? So what was the thing you noticed?
How you want to like.
This is actually like moving. So what we kind of like made several inferences, but one that we made was this one actually shows like how MO and man are variable and like how as over time the difference like creates a new corresponding point. But this one just shows
It's just one thing. How about just one thing? So the first thing you said was it shows.
MO and D being variable.
Now m naught is a particular value. What's the variable?
The variable.
M naught isn't a variable, right? M naught is a particular value of what?
Of time.
Right, which is what's our variable for time?
Minutes.
And what's the variable? What's the letter?
M.
M, right? M. Okay, so she's saying that this shows that the variables vary. Variables vary, right? As m varies, what else varies? we got 4 variables, right? We got 4 variables. What are the 4 variables? Anybody?
L.
M, L, dm is a variable.
DL.
dl. Okay? So those are all variables. They're all varying in this situation, right? So, oh no, we don't want to go around. So, but thank you. That was a good point. This table was another thing that you saw. So variables vary. That the left. So does the right graph imply that variables vary?
No. It looks complicated if you just look at the second one.
What do you mean? It looks complicated.
Well, you start with M naught and 784.6, and somehow you end up at M naught plus DM 784.6 plus whatnot, right? And a student looking at the second one will be like, well, I can clearly see the first point and I understand it, but I have no idea where you got that second point from.
Okay. Does the graph on the right imply that variables are varying? Yeah, it does.
Well, yeah, because it's a line, which is what.
Do kids think of it that way?
No.
No, that's what we're getting at, right? That's the big point. They see that as a stick lying there on the page or on the screen, right? Also, yeah, so that line over there is supposed to convey that, and does in a static way, that variables vary, but students aren't thinking that, right? Students aren't thinking that. Okay, this table, something new besides variables vary. Okay, so the point that this on the left showing that that line is a collection of points. Where on the right, who knows what they're thinking? Again, it's a stick lying on my page, or I'm drawing, or it's on the screen. It's just a stick there, right? But that line, again, intrinsically, does the line on the right imply a set of points? Absolutely, it does. But students aren't thinking that. Students aren't thinking that. They're just thinking it's this stick. Okay, do you guys think of something different? So variables vary. A graph is a collection of points. What else? Anything else? You guys think of anything else?
The triangle also emphasizes the change in M and the change in L.
All right, good. Yeah, so this one on the right, on the left, it takes your attention to starting from M naught. There's corresponding changes of M and L. DM and DL are the corresponding changes of M and L. Are those implied on the right graph? They're not shown. But they're there, right? All those same changes are there, but students aren't thinking about them. Okay? Did you guys come up with anything else? You have the toughest task. Is there anything else?
All right. So one thing we pointed out, well, I guess in my current class, they're having trouble distinguishing between increasing, decreasing, positive, negative, all that stuff.
Okay.
And on the second one, all you see is a line, but you don't see anything happening to it,
Okay.
so you don't know is it increasing, decreasing if you're starting out. Whereas the one on the left, you can clearly see it going upwards, so it appears as if it's increasing, or shows that increase.
So we're talking about y values. Are the y values increasing? Yeah. So in the right graph, are the y values increasing as x increases?
Yes.
Absolutely. Again, whether students are thinking that, some are. Okay, some are, but some aren't. Okay. So I just want to point out to you that in all textbooks, what do we see? Right or left? Right. And so do you think it's valid? All these things that you brought up about this, do you think those are valuable imagery for students to have in covariation? Yeah. Variables vary. And there's one more thing that you guys didn't touch on, but I'm not saying that you would have. But the idea that there was a moment in time when she was mowing this lawn, and as she was mowing this lawn, this was happening. Like this was being created, right? So as she's mowing, every time she mows a little bit more, there's another correspondence point of how much time has gone by and how much lawn she's mowed. And so again, when you look at the right-hand graph, are they thinking, oh, there was a time when she mowed the lawn and this graph was emerged, right? It doesn't just drop down from the sky. You know, there was a time that this happened, and when it happened, this is how that graph would have been created when she was mowing. Okay? And so all these are like really valuable things in terms of covariation. And so how can we get our students to, when they see this, they're going to see this all their lives, think this, right? That's our big challenge. To get them away from the shape thinking of, it's a line, and it's got a y-mx plus b equation, and here's, I can find a point on it, another point. Instead of thinking very statically like that and very formulaic, thinking, oh, this is the covariation of two quantities, and there's all these correspondence points being generated as the lawn got mowed. And so we could think about starting from an initial time and think about the change in time and the corresponding change in lawn mowed and all those things, right? So how do we get students to, when they see this, think this, right? Think this. Suggestions. How do we get students when they see graphs and they're going to see them all their lives like that? Think this way. No small task, huh? Yeah.
Shot in the dark, you could make it as for every little moment you make the change in the moment and the change that happens, and then a dot, and then a change that happens and a change that happens and a dot, and
Yeah,
start
so
introducing it to them.
have them physically kind of recreate this. Sure, that's a good little task. So have them, understanding how DM and DL are related and the constant rate of change, have them kind of take 10 or 15 minutes to kind of by hand create that animation. Yeah, that's a good suggestion. What else? So kind of obviously you could have this as a didactic object and have a conversation with them. That would be really helpful. Use something like that and have a series of questions to see how the students are thinking about a line versus do they think about it this way? And how in your series of questions can you move them toward thinking this way, right? Any other thoughts? Yeah. Mm-hmm. Right. This is really a much bigger question about the whole curriculum that you're using, right? Are you using a curriculum that supports covariational thinking and working on changes and constant rate of change as the proportionality of changes, dl equals rate times dn? Yeah. So it's not gonna happen in 15 minutes or half an hour, but something like pathways is a good example of a curriculum that's trying to support changing students' thinking to be more like this. Any other questions or thoughts? Okay, and so then we're learning how to use GC so that when you're a teacher and you get ideas about how to change students' thinking from right to left, you're like, oh, I could use GC. And if I've showed them something like, in your own mind, I'm not saying this, but you come up with something on your own and then you have the ability to create the animation. That's the goal of this class. So you can have a conversation to help them see, for instance, lines as covariation of two quantities. Okay? Because that's exactly what I did, right? So I'm thinking, how can I get students to interpret lines in a certain way or have a certain image of lines? And then, I thought about this. And I thought, okay, that would be really cool. After they take the quiz, I'll show them this and we'll have a conversation. So that's what I did with my calculus students. So my calculus students were doing constant rate of change. They took the quiz, and then I showed them this and had a conversation about that. Again, I don't expect that was radical. That resulted in radical changes among many of my students. Maybe it helped a little bit. Okay. again, because it's a systemic thing, right? It's years and years of seeing graphs statically using shape thinking that we're trying to undo. That's not going to happen in a day. Okay. All right. But yeah, every GC animation that I've created and used over the last 8 years was, I had an idea about what I wanted to teach, and so I just figured out how I could get GC to show it. And that's the idea with GC. All right, so let's go to the sheets on your table. The side with the 3 graphs. Start with that. Okay, so we are on a kind of a long journey of a cohesive set of ideas here, starting with where we're at. So what you guys did in your assessment on Thursday, constant rate of change, right? So we're talking about constant rate of change. So here's the next step in that journey. So a tub has 2 gallons of water in it. The faucet is turned on such that water flows into the tub at 1.5 gallons per minute. Let T be the time in minutes since the faucet was turned on, independent variable. For each graph, which is described below the graph, label the axes with the correct units, and then sketch the graph that the label below the graph is telling you to sketch. Okay? See how we do. This should be pretty straightforward. Take a couple minutes to sketch these graphs. Rate of change, right? What does a constant rate of change graph look like if it's graphing rate of change? If it's constant rate of change, horizontal line, right? A horizontal line, okay? And then we want to distinguish between, so this is our rate of change function on the left, and then over here we have 2 types of accumulation functions. So let's distinguish between those 2. So this is kind of the journey we're on. You know how fast something is changing at every moment, and you want to know how much of it you have. So you know how fast something is changing. Which of the 3 graphs would represent that? You know how fast something is changing. Left or right? Left. Rate of change, right? A rate of change function or a rate of change graph would have the information of you know how fast something is changing at every moment. In this case, how fast what's changing, how fast how fast the tub is being filled up, right? And then you want to know how much of it you have. So which of the 3 graphs is that?
Bottom right.
Yeah, so technically it's bottom right, but really kind of both of them are they're like twins, right? They're both about how much we have, right? All right, so this first one is our rate of change function. It tracks the rate at which a quantity changes. So it's a function, so given any time, so what does, and this line consists of what? A bunch of points. So here's the point, 3.3, comma, is it 1.5? What does that point mean?
It means that 3.3 minutes, it's still at 1.5 rate of change.
Right. So at 3.3 minutes after we turn the faucet on, the rate of change is 1.5 gallons per minute, is that right?
Gallons per minute.
Okay. Fabulous. All right.
So you don't have labels on your axes? Do you want to,
Well, it's not really the emphasis of this slide. But yeah, technically we should have units, right? So when you label axes, you should always label them with the units. So that's what we should have there. That was one of the tasks I gave you, though, right?
Yeah.
Okay, yeah. So mine doesn't have labels. So -5. Okay, so you know how fast a quantity is changing every moment, and you want to know how much you have. So there's 2 versions of what you have. The first one is what we're going to call net accumulation. What is this? This tracks the amount of total change, right? So here's the point 2, 3. Leo, what does that point mean? 2, 3 on this graph. Yep. Yeah. So since 2 minutes, 2 minutes into the tub being turned on, we've gained 3 gallons, right? And so this is what we call net accumulation. or the amount of change, right? It's like total amount of change. Okay, and then the bottom one, what would we call that? It's also accumulation. That'd be total accumulation, right? That includes any accumulation we had before whatever our starting point is. So it's tracking the net accumulation, but then it's including any accumulation we had prior to whatever we're calling our starting point. In this case, that was 2 gallons, right? We had 2 gallons when we said go, right? Or when we called this start, which was time equals 0. There was already 2 gallons. That gets included. And then we get a total accumulation point, function. So here's the 0.336. And so yeah, what does the what does that point mean?
At 3 minutes, we have 6 gallons in the tub.
Right. The total accumulation of water now is 6 gallons in the tub. Perfect. Okay. All right. So this is pretty easy when the rate of change is constant, right? You guys just wrote it down in a minute or two. What makes it more challenging is if we have something where oftentimes rate of change functions have a continually changing rate of change, right? And so that's really the quest that we're on, is given a changing rate function now, how much do you have? What's your net accumulation function, or what's your total accumulation function? Okay, so here's an example. Function R sub v. So R sub v gives the rate of change of volume of oil expelled per day by a rig that begins leaking at t equals 0 days. So the rig starts to leak, and then here's the rate of, this graph is the rate of change of oil expelled into the ocean. So let's just imagine, could you imagine the function v that gives the total amount of expelled oil x days after the rig started to leak? So now this would actually be the net accumulation and the total accumulation would be the same, right? Because at time 0, there was nothing. So now what we made the distinction before, now these two would be the same. So can we just sketch our goal? Our final goal would be to come up with function v. So based on this rate of change graph, can we just get a rough sketch of that? Get a rough sketch of that. I'm not sure if my next click is going to show. Do you have something very good or very close? So here's what it is, truly. Big reveal. So what's true about the amount of, as days go by, what's true about the amount of oil expelled? Generally first? Okay, but over the whole thing, is it always increasing, sometimes increasing?
Always.
And how do we know it's always increasing?
It's positive rate of change.
The rate is positive, right? So this thing is always going up, right? This thing is always, volume is always increasing. So that graph is always heading up. Right. Where? So at what? How many days is it close to being linear?
About 1.4 and 1.5.
Okay.
It's like sort of linear for a bit.
You mean horizontal?
Yeah.
Is it horizontal at 1.3 or 1.4?
The rate of change is horizontal, but
No, it's not horizontal.
the function itself is like linear.
Oh, because it's a minimum, right? So yeah, because you have a minimum on your rate of change graph. Yes, right. You get an inflection point. But is it horizontal? That's kind of a bigger question right now. So does it flatten out?
No.
Because
It doesn't hit 0.
yeah, the rate is still positive here, even though it's the lowest here. It's still positive, so still going up, Okay, so now that was just a sketch to kind of get an idea of where we're headed. We want to actually build the function v exactly. That's our goal. So if we knew exactly what r sub v was, could we actually come up and create that function v exactly? Again, you know how fast something is changing, you want to know how much of it you have. So this is the goal. Given the rate of change. Okay. So let's make sure we have a good, so our endeavor is to develop a quantity like function v given its rate function r sub v. So here's a statement, r sub v of 0.7 equals 9.68. Okay? So make sure you, so the question is, how does that relate to the graph of r sub v? How does that statement relate to the graph of r sub v? What's that? Okay. So at 0.7 days, the rate of change is 9.68 meters cubed per day. But how does it relate to the graph? How does it relate to the visual? So that's a true statement, interpreting that. But how does it relate to the graph? Yeah, right.
Which graph are you talking about?
So how does the statement relate to the graph of r sub v? Right. It's a correspondence point on the graph, right? Is that on there? Yeah, so look. So at 0.7, you get the point. 0.7, 9.68. That's a point on the graph, right? So that's showing a point on the graph. And it means what you guys said, right? That at 0.7 days, the rate of change is 9.68. So it means that at the moment, 0.7 days, the oil leak is essentially a constant rate of 9.68 meters cubed per day. Okay? What does a constant rate of 9.68 meters cubed per day mean? What does a constant rate of 9.68 meters cubed per day mean? Okay? Okay, they put it together up here. How about someone else? Good job. Kylie, you want to try it? What does 9.68 meters cubed per day mean? Okay. Cha-ching. She got it. She nailed it. Now we have to. Now we've got to add one little stipulation though. There's something else we have to say about this. Okay, yeah. So this only is really valid for like a small time around 0.7. As soon as 2 minutes time goes by, the rate changes, so that doesn't apply anymore. So yeah, so we have the same meaning we had before, but we have to stipulate or put this condition on that it has to be a small change right around 0.7 days, right? So we can show that like this. So I've zoomed in at 0.7, and I'm showing the actual rate graph. If we want to think of it as a constant rate, then what is how we're really thinking of it? How would I adjust that graph so it's how we're really thinking of that meaning for 9.68 meters cubed per day? Right. So what would it be, Brandon? So now I want to, so if it's for any change in days close to 0.7, we're thinking of it as a constant rate of 9.68. Yeah, so all lines are straight, so horizontal line, right? Horizontal line. I've got my money's worth out of that.
What is that red one on there for then?
So what's the red one on there for? So let's discuss. What's the red one and what's the blue one? Go. What's the red one and what's the blue one? Talk at your table. Talk at your table. Yeah, so look, I'm zooming in. 0.696 to 0.703. So it's a really small little window around 0.7. So if we have the exact rate as this red graph, why do I want to replace it with the blue graph? Why do I want to replace it with the blue graph if I have a more accurate? So the red one's kind of more precise, right? It's kind of, this is what's actually happening. So why do I want to replace it with the blue one? No. Okay, but, all right. We really haven't talked about the R graph yet. Why do I want the blue one if the red one is the real graph? No, we definitely do. Because what's our goal? Our goal is to do what? Our goal is not rate of change. What is our goal? Accumulation. Our goal is accumulation. So how is it that the blue one is helping us with the goal? Okay. Can you calculate how much increase in oil you got for this changing rate? Can you calculate that? Leo? Right. 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 And that, okay, which allows us to do what? No, I just want to talk about this interval. Why do we want the blue one in this interval? And not the red one? If our goal is amount of oil added, say in this little amount of time, so I guess I charged you. According to the red graph, compute for me how much oil was added. According to the blue graph, compute for me how much oil was added in this amount of time.
This is an average exactly what it is. The red graph. The blue graph says exactly that it's 9.68. The red graph is still changing, so you can't actually say what it is.
Okay. Okay, I got a nod back there. Yeah.
The blue graph shows exactly what it is, whereas the red graph you can't say what it is because it's still changing.
No, but that, okay.
Did I say that wrong again?
It's not that you said it wrong. It's the idea is, what is the advantage of the blue graph? What is the blue graph going to allow us to do that the red graph doesn't? Sophia?
Since we're saying that it's staying constant for that interval of time, we can then multiply like that change in time by the rate to
Right.
get actual.
Right. We can actually calculate. How do we actually? We can actually, using the blue graph, we can actually calculate a little change in oil. What would it be? Not dV is 9.68 times. D, is it X? I don't know if I named. We'll say dx. So now I can actually, in this little time interval, by using a constant rate, I can use my constant rate of change mathematics to get a little bit of oil added, because that's our goal. Is we want to figure out how much oil is accumulating. But with a constantly changing rate, like Leo said, as soon as I go a little bit and I change a little bit, my rate is continually changing. I can't use this unless I do it an infinite number of times, like he said, right? So by assuming a constant rate over this very short interval, I can apply this easy mathematics to get a little bit of volume. Super important concept here. So that's why we want the blue one, because it gives us a way to actually calculate some amount of volume, whereas the red one doesn't. Does that make sense? So let's do it. Okay, so suppose that, I'm going to give you some information here. At V of 0.07 is 13.15. Under our assumptions, let's go right to the second one, because it's easier to draw. And you can, if you want to work on the first one later, that's fine. We'll go right to the second one here. V of 0.7 is 13.15 total meters cubed expelled, then what are dx and dv for finding V of 0.702? So what would dx be? What would dv be? And then I want you to find V of 0.702 according to the dx and dv that you came up with. Is the task clear? See if you can do it. So at we know that. So here's your given. You know this. We're supposing that this is how much we've got at 0.7. So our goal is to find V at 0.702. So first determine dx and dv, and then so hint. Use stuff we've learned in the course so far. So someone start me off. I'm going to create this visual to reflect this calculation you guys, or set of calculations you did. So how do I start that? Jessica, can you start me? I'm going to create a picture down here to reflect this process here. Where do I start? Okay, I actually did that already, 0.75, 13.15. Okay, and so, okay, but so what happened for me to get from 0.7 to 0.702? And the line represents, right, change in x comes first, right? Change in x comes first. Okay, and that's our dx. What is that? 0.002. Okay. Then what's next? Andrea.
Yes.
So we got the change in x. What comes next? Can I call it v?
Yes.
And how do I get the change in v?
You're going to start from the end point of your dx line, and you're going to go up.
Do I know how far? Do I know how far to go up?
I don't have the number, but I can tell you how to get it.
Okay. Yeah. Yes. Process is always.
You go up to 9.68 times 0.002.
Good.
Whatever value that happens
Good.
to be.
dv equals mdx. So we're going to take 9.68 times the 0.002. Is this feeling familiar? Change in x first, then change in y. Okay. And then anyone get that number? No, just the change. So 0.069, 0.019. Okay, and so here I go, dv. I'm going to, as dx increases by 0.002, v increases by 0.019, taking me to?
Close to 13.72? It's like 13.
Almost there? And how do you get that 13.1? So vf equals?
9.68 times 0.002 plus.
Yeah, that was, remember, v initial plus dv. Final value of a quantity is the initial plus the change. And that's where you guys got the 13.169. You added that to the 13.15, right? So 13.15 right there plus the change 0.0019 gives us the final value of v. Okay. Are there any correspondence points in between those two? Tons, right? Tons. How can we represent any or all of those?
Putting lots of dots in between.
And how would can we build that up? So I want to build up or generate something that represents all the points that happened in between as dx increased by 0.002. How would I start that? now I want to get all of them. This is what lots of you missed on the quiz. How do I start this? Arbitrary point. Arbitrary point, right? I'll do black. So we're going to start with an arbitrary point. What are the coordinates of that? XV. Start here with what? How does this process start to find any XV? Dx. Good. X minus 0.7. Good. Then? Which is equal to 9.68 times. Finally? Still gonna run out of room. 9.68 times. And that's my final point, XP. So there we go. So now we got a representation of every point in that moment. So all these points. Which is a lot faster to draw with a continuous line, right? But we know what it means. Those, we got an infinite number of points that were generated as time went from 0.7 to 0.702. And all those points can be represented as v equals 13.15 plus 9.68 times x minus 0.7. Okay, so if we wanna build up the accumulation function, and we want to do it this way, right? So we want to look at these small intervals. This one went from 0.696 to 0.703. So all we need to do is keep doing that repeatedly from 0 to 2 days. What do you think about that? Should we start? Do we have time? We got 6 minutes left. So what do you think? What's wrong with that? Too enormous of a task, right? Because this interval is so small. So we did a lot of profound work here, but over this incredibly small amount of time, right? Yeah, and that was basically for this, like, really just around this one little point right there, okay? And we got this accumulation of oil for that one little point. So instead, we want to kind of start over, and we want to break up the rate function into larger intervals and do the same thing over larger intervals. So we can at least get something that's for the whole 2 days. So what I want you to do is, any questions on what we did for the little interval? Okay. So what I want you to do now is back to the rate graph. So let's make a new graph out of constant rates. We know constant rates are key, right? Because it allows us to actually calculate some amount of accumulation. Without a constant rate, there's no way we can get an amount of oil. So we want to constant rates over intervals of 0.5, such that we're going to use the rate at the left side of each interval, the real rate at the left side of each interval, to be the constant rate for that whole interval. And then I want you guys to write, and we're going to call this just plain old R, okay? So just plain old R of x. And what kind of function, how would we write that? What kind of function will that be if we're doing constant rates over intervals of 0.5? So what will be the structure of that function when I write it down here? Piecewise, right? It's going to be in pieces. Quick, do it. Okay, so we don't want to estimate these rates that we're using. We want to represent them exactly. So again, did you get the task? Using intervals of 0.5 We want to create constant rates in intervals of 0.5 such that the constant rate comes from the actual rate at the left side of each interval. And we want to write this down exactly. We don't want to pick off estimates. We want to write something that gives us those rates exactly. So here's the beauty of this task that makes it easy. This rate function is made up of constant rates. So a piecewise function is made up of constant functions. That's the easiest kind of function there is, right? It's the easiest kind of function there is. Not linear function. Well, it is linear, but easier than that, constant functions. Okay. Yes, so 1, 2, 3, 4 intervals. And we want exact representations of the rates.
So are we basically graphing that rate of change again?
Not graphing anything. Where you guys are writing down the rate functions. Exact rates.
Oh, okay, so it is just the rate of change. So
Yeah, it's a new rate. It's a rate function, which is going to be made up of constant values, constant rates, over intervals of 0.5. No, don't estimate values. I want you represented exactly.
Yeah, well, RV of 0. I thought we stopped at. No, I think we said stop at 2, right? Yeah. So that means we stop at 1.5 because that's the left side of that interval. Oh, okay.
So, what's our first constant rate? How about Noelle? What's the first constant rate? She wants RV of 0. Is that what you guys got? No response. Is that what you got? So in the first interval, we want a constant rate that's equal to the rate at the left side of that interval. What is the rate of change at the left side of that interval? The real rate. What is that rate right there? No, not an estimate. I want an exact representation of that rate. Yes, did you see it? No? So RV of 0. And then I want that for what interval? So what interval do I want RV of 0?
From 0 less than or equal to x less than or equal to 0.5.
What's my next constant rate that I want? Kelly. Second interval. What constant rate I'm going to have in the second interval? So in this interval, I want to pick off the actual rate at the left side and use that as the constant rate the whole way. So, yep. I want whatever this rate is right here. Whatever rate that is right there, that's R sub v of 0.5, that's what I want. Okay? And now, this is going to seem a little weird, but we want that from 0.5, strictly less than x, all the way up to 1, and we'll learn why next week, okay? So we're actually going to pick off this rate at 0.5, but in this new rate function, we're not going to use it at 0.5, just starting right after 0.5. Okay, what's the next rate? And that's from? And then? And so let me sketch that really fast and ask you, why in the heck are we taking this beautiful rate function and butchering it into this thing which is not accurate at all, right? Do you see how this rate function is trying to be like R sub v? Doing a good job or not? Okay, so we're taking the red rate function function, and we're saying we'd rather have the black one. Why in the heck would you rather have the black one than the red one? What's that? More than easier. Possible. Without constant rates, we can't calculate amounts of accumulation. So we're butchering this and making it into constant rates that are trying to pretend to be like the red one, but they're constant so that we can actually now make some progress at calculating amount of volume. Okay, your next